If we could travel back 4.4 billion years in time to a chaotic era when the solar system was still in its infancy, we would encounter a landscape far more violent and far more alien than the one we know today. It began with the collapse of a colossal cloud of gas and dust. As the young sun ignited at the center, the remaining material flattened into a spinning primordial disk. In the outer reaches of this disk, a gargantuan gas giant began to take shape, Jupiter. As Jupiter rapidly devoured the surrounding gas and dust, it formed a subdisk of its own, a miniature version of the solar system itself. And there, at the heart of this swirling debris, the moon we now know as Europa was born. Europa's formation started with the slow, steady accumulation of gas, dust, and ice particles, all drawn together by the relentless, invisible pull of gravity. As these materials merged and the moon's mass grew, a fierce heat began to build deep within its core. This mounting internal energy caused the interior to melt, differentiating into distinct, heavy layers. At the end of a long, cosmic process, heavy elements settled at the center to create that solid, rocky core, while the lighter water and ice formed this glowing ice crust and the massive ocean below. This was the birth of the icy world of Europa as it appears today. Looking at Europa today, we see a world completely stripped of that primordial turbulence, transformed into a silent, colossal sphere of ice. Yet, hovering just above this massive icy armor is a fascinating atmospheric phenomenon. Unlike Earth's thick, protective sky, a rich blend of various gases, Europa's atmosphere is an incredibly thin, invisible layer composed almost entirely of pure oxygen. But what is oxygen doing on this frozen world? When we think of the oxygen we take in with every breath here on Earth, our minds immediately turn to plants, forests, and microscopic life in the oceans. Earth's oxygen is the direct result of a biological process, photosynthesis. Life shaped our atmosphere. But the source of Europa's tenuous oxygen veil is not life, it is Jupiter itself. Jupiter possesses one of the most powerful magnetic fields in the solar system. This colossal magnetic dynamo traps charged particles, accelerating them to near-light speeds to create a deadly radiation belt. As Europa completes its orbit, it is relentlessly bombarded by this radiation. When these high-energy particles slam into Europa's icy surface, they literally tear water molecules apart. The bonds between the hydrogen and oxygen atoms are shattered. Because hydrogen is such a light gas, it easily escapes Europa's weak gravitational grasp, bleeding out into the vacuum of space. The heavier oxygen molecules that remain linger close to the surface, forming this fragile atmosphere. Europa's oxygen, therefore, is not the byproduct of a biological process. It is the result of a violent physical collision between intense radiation and solid ice, a purely chemical dissociation. But what is happening in the hidden depths of this moon, where surface temperatures plunge to a bone-chilling minus 160 degrees Celsius? To understand Europa's geological structure and internal dynamics, we must look to its physical relationship with Jupiter. Europa does not orbit its host planet in a perfect circle. Its path is slightly elliptical. Furthermore, it is locked in an orbital resonance with the other large moons, Io and Ganymede. This celestial dance causes Europa to be stretched by immense gravitational forces as it approaches Jupiter, and to relax as it moves further away. Just like repeatedly bending a metal wire causes it to heat up, Europa's interior is warmed by this constant stretching and squeezing. We call this phenomenon tidal heating. This tidal heating generates continuous churning within the moon's deep mantle. The immense frictional heat radiating from the rocky core and mantle is conducted upward. Just beneath Europa's ice-covered surface, kept liquid by this very heat, lies a colossal ocean. And while it has never been observed directly, the evidence for its existence is overwhelming. It is not just the mantle, but also convection currents within the ice shell itself that contribute to this dynamism. Warmer ice from below slowly rises, while the colder ice near the surface sinks. This slow but perpetual cycle balances the energy within the moon. Europa's famous outer crust, boasting the smoothest surface in the entire solar system, is a direct result of these internal dynamics. You won't find towering mountains or deep craters here. Even though this ice shell appears as a massive armor, some 15 to 25 kilometers thick, geologically speaking, it is remarkably young. The scars left by meteorite impacts are erased over time, as liquid water or slushy ice from below upwells and freezes over. The most prominent features on the surface are the thousands of kilometers of dark fractures, wrapping around the moon like a vast web. These cracks, known as lineae, are formed when the ice fractures under the rising and falling tides of the ocean below. When water seeps through these fissures and meets the freezing surface, it solidifies instantly, creating fresh terrain. But the most staggering revelation lies beneath this icy armor, a salty, liquid ocean enveloping the entire globe. Estimates suggest this abyss could reach depths of up to 100 kilometers. This means that Europa, a world just a fraction of Earth's size, could harbor more liquid water locked beneath its surface than all the oceans on our planet combined. In a place where water is so abundant and in liquid form, one grand question immediately comes to mind. Could there be life beneath this ice? For life to emerge and sustain itself as we know it, there are three fundamental rules: a liquid solvent, chemical building blocks, and an energy source. Europa generously fulfills the first two of these conditions. While its colossal oceans provide the water, the moon's chaotic formation process and ancient meteorite impacts have long since supplied the necessary chemical ingredients. However, sunlight cannot penetrate kilometers of thick ice. Under these conditions, an ecosystem driven by photosynthesis simply cannot exist. The energy source must come from elsewhere. It is at this point that we turn our eyes to Europa's ocean floor. If Europa's deep ocean is in direct contact with the rocky, active core beneath it, a continuous chemical reaction must be taking place between the water and the hot rock. In the deepest, darkest depths of Earth's oceans, there are hot water springs gushing from the fissures where tectonic plates meet, hydrothermal vents. In these pitch-black regions where sunlight never reaches, incredibly rich ecosystems thrive, fed by our planet's internal heat and chemical energy. The bacteria here generate energy using seemingly toxic chemicals like sulfur and methane, a process known as chemosynthesis. If similar hydrothermal vents exist on Europa's ocean floor, the energy needed to spark the flame of life is already there. Furthermore, if the oxygen created by surface radiation is gradually transported down into the ocean through cracks and circulation within the ice, this possibility of life becomes vastly stronger. So, if life does exist here, what might it look like? Of course, based on current scientific data, it is highly difficult to speak of advanced, large organisms. However, the prospect of finding single-celled bacteria or simple multicellular life forms colonizing around hydrothermal vents, much like Earth's extremophiles, microorganisms capable of surviving in immensely harsh conditions, is deeply thrilling to the scientific community. NASA and the scientific community are well aware that these possibilities are more than mere theories. The early photographs captured by the Pioneer and Voyager spacecraft in the past, combined with the magnetic field data gathered by the Galileo probe during its years in the Jovian system, have largely confirmed the existence of this ocean. Yet, to definitively prove the nature and habitability of this hidden sea, more is needed. To this end, NASA launched one of the most important exploratory missions in human history, sending the Europa Clipper spacecraft into space in October 2024. Scheduled to arrive in the Jupiter system in 2030, this probe will not land directly on Europa, but will perform dozens of close flybys. Armed with advanced ice-penetrating radars, it will map the depth of the ocean and the thickness of the ice shell. More importantly, it will fly directly through the plumes of water vapor believed to be erupting from Europa's surface into space, analyzing the chemical makeup of the ocean firsthand. While these missions may not hand us a direct photograph of life, they will definitively establish whether Europa's ocean is a chemical laboratory capable of supporting it. If life has managed to take root in these dark waters, billions of kilometers from the Sun, it will prove that life is not merely a miracle unique to Earth, but a universal rule